Hi everyone, so in this video, I will show you how to use a 7-segment display with our PIC 16877A, again coded in C or in XC8. And as you can see here, I have a code on my microcontroller which displays the 10 digits on our 7-segment display, that's from 0 to 9. So we'll start with a single display and then we move on to 2 displays and then to 4 displays. Okay, so just a review on 7-segment displays. There are actually two general types. We have the common cathode and the common anode. So basically, a 7-segment display is just a series of diodes or LED wired together, and through a different combination of which LED to turn on, then you can generate whatever digit you would like. That's from 0 to 9, and you can also actually display letters in the hexadecimal numeric value like A to F. But here we'll limit ourselves to the digits 0 to 9. And this is normally how a 7-segment display is wired. So we have here the letters assigned for each segment. So commonly, A is the one on the very top. Then we go clockwise from here, and we go alphabetically. So this is A, B, then you have C, D, E, F, and the last segment is G. Sometimes the last segment is the dot. So it depends on if you will be using the dot or not. Okay. So each of this segment has its own pins. Okay, and also it's common. So if you have a common cathode display, the common is wired to the ground, and that means the segments should be high for the particular segment to turn on. If you have a common anode display, then the common should be on the positive source, and for each segment to turn on, you must put the pin into a low state. Okay, and just a review on how to display each numbers. So this is 0, okay, this is 1, this is 2, 3, 4, 5, 6, 7, 8, 9. So this is the 10 digits 0 to 9. So basically, if you can look at our schematic diagram again, the way to display the digits is that for this one, by the way, this one is a common cathode display. So we have our common to ground. So to display a particular digit, we just change the state of the pin that we want. For example, we want to display 2, the digit 2. So for the digit 2, the segments A, B, D, E, and G should be high with respect to your common cathode. So if your 7 segment is wired like this, wherein your A, this is by the way A pin, is wired to RB0, and your G pin is wired to RB6, then to generate 2, you just need to make your A pin and B pin high, your C pin low, your D pin and your E pin high, your E pin low, and then you have your F pin low or G pin low, G pin high, so that you can display the digit 2. And the rest is true for the other digits. For example, if you want to display the digit 8, this is the simplest digit to remember because it actually turns on all the segments. So if this is the case, then all the pins from RB0 to RB6 is high with respect to the common ground. Okay, so this is the code for the circuit I just showed. This is again in C or in XC8. So of course we start by defining our crystal frequency or our oscillator frequency. So this time I'm using 4 megahertz. Then we include the XC8 library, of course. Then for this particular example, I only have one function, my main function. Okay, then based on our schematic, we are using port B, and all of these pins are output pins since they are generating current to our 7-segment display. Therefore, I'll just declare trace B equal to 0. So this will make all port B pins as output pins. And then to make the displays of digits looping infinitely. I created a while one loop. This is an infinite loop. And then this will be the parts wherein each of the digits from 0 to 9 will be displayed. So this is equivalent binary value for displaying the digit 0. Okay. So the way I read this one is that this is your A segment and this is your G segment. The last um, digit or binary value or bit value is actually unconnected. So for all of this from 0 to 9, the last or the MSB, the most significant bit is always 0 unless you use this for other functions like the dot. So this is the binary equivalent for the digit 0. So this is A, B, C, D, E, F up to G. And this is 1, this is 2, this is 3, 4, 5 up to 9. And each has, between displaying the digits, I have a delay of a second so that it looks like we are counting from 0 to 9 every second. Okay, so this is that code. This is the output of that code. So basically, you are counting from 0 to 9 with the second in between counts. Okay. Of course, we can modify this code. You can make this much more usable if we'll create a function wherein we can just pass a number to that function and return the equivalent 7 segment binary value. So this is what I will show you now. So I'll create a new function here. Let's say since we are only using 8 bits, it's 1 byte, so I can just use a char return type for my function. Then I will name this function um, number to segment, and it will accept a number as a parameter. So what this function does is it will return the equivalent binary digit for every number that is passed to it, and that number should be from 0 to 9 only. Okay, so I'll just copy this part right here. Okay, I'll copy this part right here, paste this one inside the function, and then I'll just remove the delay. We don't need the delay here. Okay, I can remove the delay. So basically what happens here is that depending on what value is passed on this number variable, then that would be, and the corresponding binary value will be returned by the function. So I will be using case here. Okay, so that will be switch number that. Then case is 0. That is when number is 0 or the value passed to this function is 0, then it should return this value right here. Right. So let's just copy this one. Right, so it says return that. Okay, then of course we need to break the case. Then case 1, so we'll just continue this until we reach 9. Alright, so this should do it. So to call this function, of course we just need to call this function name here. So on our infinite loop, instead of doing this, we can just do can actually create a for loop. Okay, so this loop will be from 0 to 9, and of course we start with I equal to 0. So in this loop, we call the function number to 7 segment. Okay, then we pass the value of I. So we'll start with I equals to 0, and it will convert the digit 0, and it will return the equivalent binary value for the segment display. This would be it. This would be the equivalent for 0. And then whatever the value passed would be the value for port B. We can just assign this function value to port B. Then again, we use a delay of a second between digits. Okay, so as you can see, this is a much shorter code, and with this we have a usable function that we can use in another example later on. So let me just compile this first. Alright, so that's successful. Actually, I don't need to copy this hex file link anymore, but just to show you that we'll be updating our code. I'll do that again here. Okay, so let's paste this one. Alright, so it's basically the same output, but this time we are using a function to convert any number from 0 to 9 to its equivalent 7 segment display. Okay, so I added another digit to our 7 segment display. So this time I'm using a dual 7 segment display, still a common cathode 7 segment. So this time the segments for both these digits right here are connected in the same wire. That means that the A segment here is the same as the same connection as the segment A here, and this is true for segments B up to the segment G, and also for the dot. So what happens here is that you only have A to G pins for both. Okay, one A to G pins for both, but you still have your separate common pins. In this case, a common cathode for digit 1 and digit 2. So basically, this is the common cathode for this one with the 1 here is the common cathode for digit 1. And this here with the 2 is the common cathode for digit 2. So what happens here is that you need to alternately turn on and turn off each segment, and then you display whatever digit you want to have. So what I did here is write a code that displays the digits 00 up to 99. So this is its output. Alright. So you notice it's flickering, right? It's because it's actually switching at the rate that you can adjust. And I made it so that we can actually see it flicker, just to give you the concept of the code. So what happens here is that your common cathodes, both 1 and 2, are constantly switching, right? And then depending on which digit turns on, then we throw a value for that digit. So basically, if this is the output, so basically you have your tens digit here and you have your ones digit here. So the ones digit increments, and if it reaches a number greater than 9, then the tens digit increments by 1. So let me just restart this one. So both starts at 0, tens and ones, and the ones will increment. Okay, and if it reaches the number greater than 9, that will be 10, then the tens digit will increment by 1. And this goes on until the tens reaches 9 and the ones reaches 9 also, and it all goes back to 0. Alright, so the tens now increments, and the ones resets to 0, then continues to count again from 0 to 9. Okay, so how did I do this? For this is the code for it. Okay, so basically, I recycled that function we used in the earlier example, number to segment. The major adjustments or changes is on the main function. So since we are now using other pins for the common cathode, okay, so my digit 1, the common cathode for my digit 1 is connected to RC0 right here. And the common cathode for digit 2 is connected to RC1. So that's the case. I added a trace definition. I have trace C0 equals to 0 and trace C1 equals to 0 because both RC0 and RC1 are output pins. Alright? Then on my infinite loop, my while one loop, I just needed to switch between two segments. So as I mentioned, the segment 1, the left digit is the tens, the right digit is the ones. Alright, so first, I set RC0, that means I put it in high state, and then I cleared RC1, so I put it in the low state. And if this is the scenario, what happens here is that the uh, the common cathode connected to RC0 is turned off, and that common cathode connected to RC1 is turned on again. I have here RC0 equals to 1, RC1 equals to 0. So we have common cathode, that means the one connected to RC1 should be turned on, so that would be the ones digit, and then the ones connected to the RC1 or RC0 pin is turned off. So when the ones digit is turned on, I pass the value of the ones digit to my number to segment function. And whatever this function returns, if we pass it to port B, that's why it will display a digit on the rightmost segment. Then I introduced about the 50 millisecond delay. Of course, this can be adjusted. This delay here is responsible for how fast the switching between digits are. So if you make this large or larger, then you will notice significantly how the segments are alternating. So let me just show you that. I will make this, for example, 1,000 millisecond or a second between. Okay, so yeah, so that's it. So you can really see how the segments are alternating, or how the digits are alternating. So it's a matter of just getting the right delay. Of course, we don't expect the same result with an actual 7 segment display in an actual or a physical circuit, since we are only using a simulation. But again, you can just adjust the delays here. So let me just revert it back to 50 milliseconds, and then so that's it. Okay. Of course, we can still make this faster to go away with the flickering, but for this purpose, I think this is just enough. Okay, so that is when your RC0 is high and your RC1 is low. So the ones digit, the one on the right is turned on. Now, the next part, we have RC0 equals to 0 and RC1 equals to 1. So this time, it's the tens digit that it's turned on. That would be the left digit. So if that's the case, I just pass that value of the tens digit to my function, number to segment, and then whatever the value returned by this function is passed to port B. So this is now the part where the tens digit is displaying a number. Alright. So what happens next is that I have actually a counter variable right here. Counter variable. Okay. So why did I use a counter variable? I don't want my ones digit to increment every time the loop goes back to the start. Right? So if I will do that, if I will remove my counter right here, actually, our ones digit will increment every time the loop goes back here on the top of the loop. Okay, so to avoid that, I added a counter so that the ones value only increments every time the counter exceeds a number. This time I set it to 15. And then again, you can adjust this. So basically, the this amount will tell you when your ones digit will increment. So if I will make this a large number, let's say 50, right? 50. So this would make the ones a digit increment longer. Okay, so this is at 50. So as you can see, it doesn't increment right away. So it waits for the counter to go 50 and then go. So it increments to 1, then it waits for 50 counts again, and then it increments to 2. So basically, the longer this value or the larger this value is, the longer the ones digit increments. And if you want to increment the ones digit per second, then you can just adjust this value to whatever you like. So let me just go back, replace this back to 15, and that would make, of course, ones increment sooner than the ones previously, where our maximum count is 50. Okay, now, so that's it. If the counter reaches 15, then your ones digit increments, then of course you need to reset your counter to 0. Now, you need to also check the value of the ones digit. Alright, so the ones digit, the digit on the right should not uh, go beyond 9, of course. So we are in a decimal system. So if ones would go beyond 9, if it becomes greater than 9, then we should increment tens, the left digit, and then we clear ones, and we make ones equal again to 0, so that the cycle repeats. Okay, in the same way, we also check the value of tens. If the tens digit, the one on the left, is greater than 9, then it should reset back to 0. Okay, so this is how we implement this counter right here using two 7-segment, common cathode 7-segment display. Okay, so this code will be shared. I just share this to you. Alright, so for the next part, I will be using 4 7-segment displays, and it would not be very different with this one because it actually follows the same principle. Whether we call this POV or persistence of vision, this is a trick. We actually are tricking the eye to make it appear as if both these two digits are turned on simultaneously, although in reality they are actually alternating. So we call that POV or persistence of vision. Alright, so this time I'm using now a 4-digit 7-segment common cathode display. So I'm gonna play this one. Okay, so it uses the same principle. We are still using POV, persistence of vision. So basically, you have 4 digits now, and if once goes beyond 9, then this will increment, right? And then I make it like a clock. Actually, this would be the seconds, and this would be the minutes. So the way for this one to increment is if this value right here would be greater than 59, or if this becomes 60, it will increment here. But again, we still need to adjust the timings, the delays, so that we can actually capture a real second. By the way, this is by no means the best way to implement a digital clock. There are better ways, particularly using timer interrupts, which hopefully I can discuss in future videos. But this is just an overview of how 7 segments work, and this is just a simpler technique in using multi-digit 7-segment displays. But design-wise, I would be the engineer, I wouldn't implement it like this. This is just a lecture or a tutorial on how this is actually done on the simplest technique possible. Okay, so we will just wait for the count to reach 60. So this we can confirm that this digit right here would increment, or the second digit from the left would increment. Okay, so 56, 57, 58, 59, and no, it didn't increment. All right. Anyway, let's start to review our code. See if where did we miss. Okay, so basically I just added two more pins because we are now using 4 digits. So in the previous one we have only up to tres C1. So this time up to we have tres C2, C3. Take note that the rightmost digit it's connected. Its common cathode is connected to RC3, and you have your third digit to RC2, second digit to RC1, and your first digit is connected to RC0. Alright, so since each of these port C pins are output pins, so you need to initialize or indicate here you have your test C0 up to C3 as 0. Then the same way, in the loop, we switch between the 4 digits. So this part right here is when your rightmost digit is on, and that would be your ones or your second ones, your ones digit for your seconds. So that's why you have here sec ones pass to the number to segment function, and then whatever this uh, returns pass to port B. So actually adjusted the delay to 35, hoping that it will reduce the flicker. But then again, since we are still using simulation, I don't expect it really to freeze like in an actual circuit. Okay, so we just do this until we reach the tens digit for the minute. Okay, okay, of course taking note of how we switch between the 4 digits. Okay, so this is when your rightmost is turned on, your third from the left is turned on, your second from the left is turned on, and your leftmost digit is turned on. And again, we use a counter. This time I adjust it to 8. Again, hoping that we can have the ones digit of the seconds increment by second. And then again, it needs to be adjusted to actually get the second of delay between the counts for the ones digit for the second. So basically, if the counter is greater than 8, then we increment our ones digit for the second, then we reset counter back to 0. Then we check the value of the ones digit for the second. If it's greater than 9, then we increment the tens digit of the second, then we reset back the ones digit to 0. Okay. So basically this is where we missed it, right? So um, if this is greater than 5, yeah, it's correct. So if this is greater than 5, then we should increment our ones. So this is where we messed up. That's why it didn't update when we reached the count greater than 60. So if the tens digit of our second, which is a value greater than 5, then our minute 1 should increment, right? And then we reset back our tenth digit of the second to 0. And then same goes for the minutes. For the ones digit of the minute, we check if it's greater than 9, then we increment the tens digit of the minute, and so on and so forth. Okay, so that should be that is the code. Okay, so let us check again since we corrected our error earlier. So this should now increment the minute, or the ones digit of the minute. That will be the second digit right here when the second reaches, or the second, both the 5 and the 9 here, or it goes to 60 right here. The ones should increment this second digit right here. Okay, so let's just wait for it to reach 60. Hopefully it doesn't take that long. Of course, that's approximately about a minute. So actually you can add more digits here. Your limiting factor is actually the number of pins for your common cathode, or your common cathode if you're using that type of 7 segment. Okay, because your segments, your A to G segments, is only using 7 pins on your microcontroller. Okay, so for example, if you're using 6 digits, then you will need 6 common cathode pins. That's aside from the 7 segment pins. Okay, you want to make 8, or you want to use 8 digits, and you need to use 8 common cathode pins. And for the 877A, you have a lot of pins to use. So basically, you can have, let's say, you want to use all port C pins, that's 8. You want to use all port D pins, that's another 8. That would be 16 digits all. Then you still have your analog pins right here. But I usually don't advise using the analog pins. Although you can use it, of course. So maybe your max would be around 20 digits, or yeah, more than 20 digits. But let's have it around 16 only. No? If we will limit ourselves to only the digital pins and not using the analog pins. This RA0, RA5, RA0 to RA2 pins. Alright, that should increment. Yeah, okay, so we are now beyond a minute, supposedly. And we have here 1 on our second digit, which is the ones digit of our minute.